Okay, let's go ahead and answer these guys. So can somebody tell me why it says NaCl in that very first cell up there? Yeah, why is it Na just in one Na and one Cl? 1 plus for the sodium, right? How do you know the sodium makes a +1 charge? It always does. So how do you know that that sodium has made a +1 charge and it's not 0? It's in a compound. So if the sodium had been written by itself and there was nothing written there, then its oxidation state would be what? 0. Because it's still an element. But I know that it's actually reacted because it's already in the compound. And then anytime sodium has reacted and now it's in a compound, what's its charge? 1. So its options are 0. For all elements, their charges could be 0 if they haven't done anything yet. Or if it's in a compound, it's going to have a charge. And in this case, I know that the sodium's charge is going to be +1 because it's in column 1. And that rule we have is group 1 metals always form a +1 in a compound. And you know the chlorine one, well, really because it says there at the top that the chlorine's charge is -1. But you also should know that because halogens make what charge? -1. Unless they're with oxygen or another halogen, which sodium is not. Okay, so how does that first cell and the next one, the first one that you're going to write right below it, how are those the same? Both the cations of the chart, I mean, everybody in that column is going to have a chlorine on it, a chloride ion on it. So we know the negative is going to be -1s. And then in this case, the cation that I'm attaching it to it is the same charge as the sodium. They're both +1, so they'd have to come up with the same formula. So this is going to have to be AgCl. And what's the name for that one? Silver chloride. Okay, great. Next one. What's this one look like? It looks the same, right? How come it looks like the first two? Yeah, the ammonium's charge is +1. So they're just going to form the same ratio. Anybody else in this column going to look like that? Not mercury. The potassium is going to. Yep. So when I'm doing stuff like this, I usually look at these ions and say, all right, that's a +1, that's a +1, that's a +1, that's a +2, that's a +2, that's a +2, that's a +2, that's a +3, that's a +7, that's a +1, and that's a +2. And so then when I'm running through this, I know that my ratios have to be the same if they've got the same cation associated with them. So what's the next one look like with the mercury? HgCl2.
So but doesn't mercury have to come in here?
Only when it's +1 charge. So the mercury's charge is +2, and I can only put things that are -1 on it. So if I've got something that's +2 and I put 1 chloride on it, then I still have a +1 charge. So I need to put another chloride on it, so that's why I've got 2 of them. I'm sorry, the name for the last one? Actually, Mary said it. What's the name for the last one? With your mouth full of fries. Sorry about that.
Real quickly, so why is the 4 there for ammonium chloride?
Because that's what ammonium is, NH4 plus.
Still waking up.
So this is ammonium chloride. And then the next one? No, I'm sorry. The one we just wrote down, what's its name? No. Yes. Mercury 2. You have to tell me 2. Why do you have to tell me 2? Not because it's a metal. Sodium's a metal. Silver's a metal. Because it's a metal that has a variable oxidation state, which most of them that are in the transition area do. Not all of them, but most of them. So which metals do I not need to give oxidation states for? All the group 1, all the group 2, and then what else?
Oh, yeah.
Zinc, cadmium, silver. And then basically everybody else needs to have a Roman numeral associated with its name, so I know which one I'm talking about. So formula for the next one. Why is it CaCl2? Just like the last one, the cations +2 and the anions are all -1. And the name for this guy? Why is it just calcium chloride, not calcium 2 chloride? It's not variable. It can only be +2. So, I mean, if we were doing this, renaming the whole nomenclature stuff, that probably would have been a smarter idea to just tell everybody that it was calcium 2 and just name every single thing's oxidation state. Then it's very, very straightforward. Instead of you having to remember which ones have variable oxidation states and which ones don't. But it's not the way it is. Maybe it'll be like that later. But when you write a chem textbook in like 15 years, then you just don't do it that way. Next one. Why is this one the same? It's in the same group, so it better have the exact same ratio. This is the reason the periodic table looks the way it does, because Mendeleev went and found calcium and saw how it reacted with chlorine, and then found other elements that reacted in the same, and magnesium was one of them. So that's why it got to be right below magnesium on the, or magnesium got to be right above it on the periodic table. Okay, so, and then this next one, same situation, because the copper's got a +2 charge. So what's the name for this one? Copper 2, because copper could be copper 1 or copper 2. Okay, and then the aluminum, what do I do here? AlCl3. So the aluminum comes +3, and so that means I need 3 of the negatives to cancel that out. And the name of this guy? Just aluminum chloride, because the aluminum's charge is fixed. Okay, next one. Mncl7. So this one's manganese 7 chloride. And then we've got the potassium chloride here, and then the barium chloride. What's that one look like? BaCl2. It looks like that because the barium and the calcium and the magnesium, they're all in the same group, so they better have the exact same ratio. All right, how about the next one at the top of the next column? Na2S. So this time the cation has a -2 charge, so I need 2 pluses to cancel it out, so I'm going to need 2 sodiums there. So since the next cation also has a +1 charge, it's going to have to look exactly, what's the name of this one? Why is this one just sodium sulfide? Sodium's got a fixed oxidation state, not variable, so you just say its name. All right, so my next one is Ag2S. And same situation, right? Silver is one of those 3 transitional metals that doesn't have a variable oxidation state, so I just say silver sulfide. Okay, next one. NH4 parentheses 2S. So this guy's name? Ammonium sulfide. Okay. So how are you supposed to know from the name ammonium sulfide, if I gave you the name, that it's NH4 and not just NH4S? Because I need 0 charge, the ammoniums are +1, and the sulfides are -2. So yeah, that's how you're supposed to know. So this next one, the mercury and the sulfur, they just go straight together, right? Because it's a +2 and a -2. So what's the name for this one? Mercury 2 sulfide. Yep. Alrighty. Next one. CaS, just calcium sulfide. And the next one is magnesium sulfide. And the next one is copper 2 sulfide. Still copper 2 sulfide. All right. And then we've got aluminum with a +3 and a sulfur with a -2. So I'm going to need 2 aluminums and 3 sulfurs to get myself to the least common multiple of 6. All right, now I've got a manganese with a 7 and a sulfur with a 2. So then the least common multiple is 14. So 14 pluses, 14 minuses. So this would be manganese 7 sulfide. And then K2S and then BAS. Okay. So I've got a sodium nitrate up there, and then I'm going to have a silver nitrate, and then I'm going to have an ammonium nitrate, and then I'm going to have a mercury 2 nitrate, and a calcium nitrate, and a magnesium nitrate, and a copper 2 nitrate, and an aluminum screw that all up, an aluminum nitrate, and a manganese nitrate, and a potassium nitrate, and a barium nitrate. The ratio of cations to the anions for the first column and the third column are the same. We get that? Because this is a -1 charge, and the nitrates are also a -1 charge. So the second column, it's going to be the same as what? The third column, this column and this column are both -2, and so is that one. I mean, this column, stop it, is a 3. Okay, so these two columns, the ratio should be the same between these. So I'm going to need 2 sodiums and a sulfate, and 2 silvers and a sulfate. So we have sodium sulfate and we have silver sulfate. And then I've got ammonium sulfate, and then I've got mercury 2 sulfate, and calcium sulfate, and magnesium sulfate, and copper 2 sulfate, and aluminum sulfate, and manganese sulfate, and potassium sulfate, and barium sulfate. And the next column is going to look basically exactly the same. Everywhere I have a sulfate, I'm going to swap that out for a carbonate. So I've got sodium carbonate, I've got silver carbonate, I've got ammonium carbonate, I've got mercury 2 carbonate, calcium carbonate, magnesium carbonate, copper 2 carbonate, aluminum carbonate, manganese carbonate, potassium carbonate, and barium carbonate. And then this last row, the phosphates are 3, so I'm going to need 3 sodiums, PO4, and 3 silvers. So sodium phosphate, silver phosphate, ammonium phosphate, and then mercury phosphate, and calcium phosphate, and magnesium phosphate, and aluminum phosphate, and manganese phosphate, and potassium phosphate, and barium phosphate. Any questions for this? Yeah.
The copper nitrate, copper 1 nitrate?
No, did I mess something up?
No, I'm just trying to figure out the Roman rules. So is that what it's called? Copper
2.
2, that one
We're talking about talking about that one right there. So what's the charge on the copper? So this entire row, every time I named anything that's in that row, what do I say? Copper 2. Every time. This one here? Mercury 2. This row here? Manganese 7. Every single time. Doesn't matter the ratios, because what you're telling me when you say manganese 7 is that manganese atom is what has happened to it. It's lost 7 electrons. All right, so we got these gray ones here. Got HgCl2, MgS, AgNO3, CuSO4, NH4CO3, and Kp. What happened? What's going on? Are you seeing that too?
Yeah.
Stop it.
Doesn't matter what order we put those in. I don't talk about.
I guess not. That is, what the hell is going on? And it doesn't even see that thing. Okay. What was the other one? All right. So the first one, what's the cation? Mercury, and it's +2 and -1. And it's mercury 2 chloride. Okay. For the next one, magnesium with a +2 charge, and sulfur. Why is this just disappearing? Cool. Oh no, it's all there again. Yay. And it's just all over the place. Evidently I can't move it. Alright, let's see if I can. Okay, so let me try this again. Mg +2, S -2. And then the next one, I've got a silver with a plus charge. I've got an oxygen with a -2 charge. And what about my nitrogen? Nitrogen is +5. Because I've got oxygen 3 times, so that's -6. And a silver with a +1 charge, and then my nitrogen's +5 charge.
So it's oxygen +2? I'm sorry.
No.
Oxygen -2.
Yeah, and so -2, -2, -2 gives us -6. We already said that there was 1 + 1 from the silver, and so then the nitrogen needs to manage the other pluses, which is there's 5 left over, so it's got to be nitrogen +5. Okay, so my copper in this case, we knew that the copper was a +2, and the oxygen is a -2, and so in this case, the sulfur's got to be a +6, because it's 4 oxygens gives us -8. 1 copper cancels 2 of those out, so then the sulfur has to manage the other 6+ charges. The next one is a little difficult as a whole molecule. All right. So what could you do instead of hitting each of those 4 different elements? How could I make this easy, a little easier on myself?
Just use the ammonia.
I could just use the polyatomic ions, right? I've got this NH4 with a plus charge, and I got this CO3 with a -2 charge. And so when I'm looking at this thing right here, I've got a hydrogen with a plus charge and a nitrogen with a -3 charge. And then with my carbonate, I've got oxygens with a -2 charge, and then this carbon must have a +4 charge. And then I can put those things together. And then the last one here, the potassium has a plus charge, the oxygen's -2, and then that makes my phosphorus +5. Yeah, +5. Great. Okay, what do we got here for these guys? Yeah, this one's, why is this hydrobromic acid? There's no oxygen there, so I have to say hydro. And then I know it's an acid because it starts with an H, and it's bromine, so it's bromic acid. So hydrofluoric acid is telling me what? This thing starts with an H because it ended in the word acid. And then there's a hydro there, so there's no oxygen, so I just need a fluorine. Okay, and how about the next one? So I don't say hydro with this one because there's a oxygen there. And what's the polyatomic ion? Carbon 8, so then it becomes carbonic acid. All right, so I have phosphoric acid. So that's telling me I've got an H starting with this because it's an acid, and then it was phosphoric, which means I'm talking about the polyatomic ion phosphate, which is a PO4 with a -3 charge. And so the H's that I'm putting in front, I'm going to need 3 of those guys. The next one is an acid because of the H, and then CrO4 is which polyatomic ion? Chromate, and it's got a -2 charge, which is why there are 2 H's. So then this is chromic acid. Acetic acid's polyatomic ion, acetic, is acetate, and I'm going to write it the way most people write it. So there's no H at the beginning of this, but this is that exception to the acid that doesn't begin with an H in its formula because it's written as a condensed structural formula instead of a molecular formula.
There's only 2 oxygen.
Yep, there's only 2 oxygen. And then the next one, I've got an H, so it's an acid. I got a bromine, so it's bro something or other. And then I've got oxygen, so I don't say hydro. So then this one is just bromic acid. And then perchloric, so that's the polyatomic ion ClO4 with a negative charge. Per, and then chlorate is where it came from. And since it's got a -1 charge, then it's just going to need this. I just don't even know what just happened. It looked like it's something. There we go. So then I just need an H in front of the Cl. Can we see in this table why it's really important to remember when and when not to use the hydro? Right? So which ones are it important for? Those are really different acids. Yay. There we go. Those are really, really different acids. But the only way I know the difference between the 2 of them is that hydro part, letting me know if there's an oxygen there or not. Okay.